Okay, so the first thing I want to do is write this in sort of a nice vector form. So x prime y prime is matrix x, y. And the matrix is negative g, negative r, s, negative d. And all of the constants, g, r, s, and d, are positive. So let me just keep that in mind. Now, there's a lot I can tell about the system, actually, by just thinking about the matrix, right? That's what we saw in the previous lecture. Say, by looking at the determinant and the trace, I can just tell a lot of things. So let's just compute those. So the determinant is going to be this times this, so GD, minus this times this, so plus RS. Okay, so that's definitely greater than 0, right? Because all of the constants GD, R, and S are greater than 0 here. So what does that tell us? Well, it rules out only one thing. It rules out the possibility of a saddle point. So I guess now we know saddle point is impossible. So that's cool. And then for trace, let's look at that. That's negative g plus negative d. So negative g plus d, let's say. G plus d is positive, so the trace is negative. Okay, that's interesting. So the determinant is positive, and the trace is negative. Now, I still don't know if I'm looking at a real or complex eigenvalue situation. If it's a real eigenvalue situation, then, and I know it's not a saddle point, then it's either a stable node or an unstable node, or one of the other like extra special cases, right? Let's think about only the non-special cases. So if, maybe I should write instead of just talking. So if real eigenvalues, then we've ruled out saddle point. So we have either stable node or unstable node. That's pretty much the only possibilities. Then there's the special ones, like if one of the eigenvalues is 0, then you have like a line of equilibria. Or you could actually have repeated eigenvalues. Okay, whatever. Those are like really special. So the parameters G, D, R, and S would have to be like perfectly arranged in some way to make that exact thing happen. But these are more usually what you would get. Okay, and then if complex eigenvalues, then complex eigenvalues are possible. If I had gotten the determinant negative, then complex eigenvalues would be impossible. So the determinant really doesn't give me any information about the complex situation, but the trace does. Oh, I haven't, oh yeah, and the trace also gives me information about this situation. So the trace is negative, so that tells me I definitely have a stable node. So if there are real eigenvalues, it's a stable node. So that's what trace told me. Determinant, so normally I could also have saddle point, right? But no, thanks to the determinant information. Okay, and then for complex eigenvalues, I can have stable spirals or unstable spirals. Or a center, right? But that's like a super special situation, stable or unstable. A stable center is a very special situation. So let me just focus on the non-special things. The trace being negative rules out unstable spiral, right? Because remember, the trace is 2 times the imaginary part of the eigenvalue. So, sorry, the trace is 2 times the real part of the eigenvalue. So the only possibilities are either we're looking at a stable node or a stable spiral, or one of the special in-between weird things. Okay, so can I figure out further? Can I figure out whether the eigenvalues are real or complex? So to do that, I need to start solving the eigenvalue problem, and then I'll just stop when I see what I need to see. So let me go ahead and try this. So I'll subtract lambda from the diagonal. So I've got my matrix. subtract lambda from the diagonal, and then take the determinant of that. So I've got negative g minus lambda times negative d minus lambda minus negative r times s, so plus r s. And then I'll do some algebra, or I'll make my computer do some algebra. And I've got this for my characteristic polynomial. Then, the eigenvalues are the roots of this. So how do I know when those are going to be real or complex? Maybe different choices of the parameters sometimes give me real, sometimes give me complex. Or maybe just because the parameters are always positive, maybe it's kind of like up here and up here, where I can be certain that I'm always in the real case, or maybe I can be certain I'm always in the complex case. Let's find out. So let's see. Lambda, so quadratic formula. Lambda is, let me just focus on the part that's important. So when you use the quadratic formula, you get lambda is stuff plus or minus square root stuff over stuff, right? Well, you only need to pay attention to what's under the square root. So let's pay attention to that. D plus g squared minus 4 times 1 is the coefficient here, times this one. dg plus rs. Okay, so we should get positive eigenvalues, or sorry, we should get real eigenvalues if and only if the thing under the square root here is positive. So real eigenvalues if and only if this thing under the square root is greater than 0. Now let me manipulate this inequality and write down some equivalent inequalities. So this inequality holds if and only if So if it's been a while since you did algebra with inequalities, basically just do regular old algebra with equations, right? Just doing the same thing to both sides at each stage, except make sure that the things you're doing preserve the ordering of numbers. So like adding a number preserves ordering, subtracting a number does, multiplying by a positive number does, but multiplying by a negative number doesn't. So the only rule you have to, I don't think it's coming up here, but the only thing you really have to be careful with is when you multiply by a negative number, you need to actually flip the ordering. Okay, so let's see. How about I expand this out? D squared plus dg plus g squared greater than 4dg plus 4rs. Sorry, this is 2dg, right? And how about I cancel the 2dg here? So we get d squared plus g squared greater than 2dg plus 4rs. And I see a chance to factor things here. So d squared minus 2dg plus g squared, subtracting the 2dg over, greater than 4rs. And I like doing that because this looks factorable. It's d minus g squared greater than 4rs. Okay, interesting. So you get real eigenvalues if and only if d minus g squared is greater than 4rs. And you get complex eigenvalues if and only if d minus g squared is less than 4rs. And what happens when you get equality? D minus g squared equals 4rs. That's the situation that's between real and complex eigenvalues. That's what we saw was called a degenerate node last time. It's the situation that I haven't been talking about very much. I kind of skipped it over. So that's where what you would have under the square root is 0, and that's repeated eigenvalues. Okay, so that's a pretty special case, but chances are if you randomly picked d, g, r, and s that either this is bigger than that or the other way around. So then, depending on d, g, r, and s, you could have oscillating solutions, or you could have a node type thing, a stable node. So you either have stable spiral or stable node. let's see if we can interpret this somehow. So let me remind myself, what are the constants d and g here? D and G are the natural decay rates, right? Yeah, D and G are like the natural tendency of your excess glucose and excess insulin levels to just go towards equilibrium on their own. And then R and S are representing the sensitivity of one to the other, how intensely they react to each other, how intensely insulin's presence causes glucose to decrease, and how intensely glucose's presence causes insulin to increase. So that's R and S. So let's think about it this way. How about I write this? So you have complex eigenvalues if and only if the flipped version of the inequality holds. So maybe I'll even divide the 4 to the other side. So I can just think of this as being a statement about the product RS. So, okay, let me remember again what were R and S. So S is like the sensitivity of your pancreas, how strongly it reacts to the presence of glucose. And R is the sensitivity of your cells to the presence of insulin. So if you are hypersensitive in either of those senses, either your pancreas is hypersensitive to the presence of glucose, or your body reacts very strongly to the presence of insulin, then this number is big. When this is big, that's when you get complex eigenvalues. That's when you get oscillating solutions. So it sounds like you get complex eigenvalues when you're very sensitive in either one of those ways. And how big does this have to be? Well, bigger than this thing. Is there a nice way to interpret this thing? I guess it's like sort of the distance, squared distance between D and G, which are the two natural decay rates. So let's say the two natural decay rates are the same, like D equals G, then this would be 0, and you would always have complex eigenvalues. Yeah, thinking about it, I'm actually not sure why that would be. I'm not sure why the difference between the decay rates, or the distance between the decay rates matters so much for whether you end up with oscillating solutions. It's kind of interesting. Okay, so let me summarize what we've found so far. We started with this differential equation system. We wrote it like this, and then we looked at the determinant and the trace. And we know the eigenvalues are either real or they're complex. In the real case, you have these three possibilities, stable node, unstable node, and saddle, but the positivity of the determinant rules out saddle. And the negativity of the trace rules out unstable node. So you can only have a stable node. And in the complex eigenvalue situation, the negativity of the trace rules out unstable spiral. You can only have stable spiral. Then it remained to know whether we have a stable node or a stable spiral. Are the eigenvalues real or complex? And it turns out the answer is, well, it depends. So we can analyze this question by looking at this thing under the square root. Is it positive or negative? And we found that the answer is, well, it depends. The eigenvalues are real, in which case you have a stable node if you have this inequality, and they're complex if you have the opposite, and then you have a stable spiral. So here's our summary. Here's our system, and if RS is small, this is like the not so sensitive person, then stable node is what we have, and if RS is big, then we have a stable spiral. Now it would be nice to see to what extent we can actually draw phase diagrams for these things, for these two different situations. We definitely cannot just go ahead and straightforwardly plot something. We cannot even ask a computer to do it. because there are parameters here, right? Like, if all I know is that RS is less than this thing, that doesn't tell me what are R, S, D, and G. They're still unknown parameters, so there's nothing really to plot. But maybe I can make a qualitatively correct picture that that communicates what all the different situations under this condition look like somehow. Well, I'm going to say this one is kind of hard. And let's come back to it. But let's look at stable spirals. That's easier because, at least qualitatively speaking, if I don't label any of the axes, I mean, so what level of complexity can there really be? In the end, a spiral is basically just an ellipse, except with an exponential decay or growth or whatever, right? And yeah, ellipses can be complicated, but if you stretch and squish your axes in a suitable way, they pretty much just look like circles. So as long as I actually do not label my axes, I can just draw circles and then just say, yeah, the tick marks are just spaced however they need to be to make my ellipse look like a circle. That really doesn't matter because I haven't even given units to anything, right? So an ellipse can be deformed into looking like a circle if you just choose the right units. You know, actually, I take it back. That's not strictly true. Never mind. I'm not sure why I said that. You can't deform an ellipse into a circle always. If your ellipse happens to be something like this, where the major axis is lined up with one of the axes, or like this, then you can, by the right choice of units and tick mark spacing, deform it into a circle. But if it's like this, then I think it will always look deformed, no matter how you choose your units. Okay, anyway, one thing we can do is draw the, so it's stable spirals, right? So we know that things are spiraling in. What I'm trying to communicate is, since I'm not labeling any axes, I don't need to get the exact right level kind of curvature. I just need to draw something spiraling in, and that gives me a good enough idea of what's going on. But I could have it spiraling in like this, or I could have it spiraling in the other way, like that, right? Clockwise or counterclockwise. And those are two very different situations. So it'd be nice to know which one is the correct one. Is it this kind of spiral or this? So one way to know is actually just to check the velocities of trajectories. You can get access to the velocities of trajectories without actually solving the differential equation. Why? Because what the differential equation is in the first place is a prescription for what the velocities of trajectories should be. That's what it is. That's like the information that it gives you, is the velocities. So like x prime, y prime, that's a velocity vector for a trajectory in the xy space, right? And the differential equation is prescribing that if your trajectory happens to be at the point xy, then its velocity should be this. So you don't need to solve the differential equation to get that. That is the differential equation. And solving the differential equation is the process of going from knowing the velocities of trajectories at all the different points to getting the actual trajectories that have those velocities. So the reason I'm talking about velocity is because the velocity vector will tell you which way the trajectory is going. And so, for example, if I have a spiral that's passing through this point, and I know it's spiraling in, then if I'm told that the velocity vector, say, points that way, then I will know that it has to spiral in like this, right? It can't spiral in going the other way. So knowing one velocity vector at one point should be enough to know the direction that it's spinning around the origin, rotating around the origin. Okay, so let me actually focus on this point. That was just a random example, but it's a good example, and it should contain enough information. So this point will be, I'm I don't know, some positive number for my x value and then 0 for my y value. How about we call it 1, 0? Let's just make that point be 1, 0. Then when x, y is 1, 0, what's x prime, y prime? It's this. The matrix applied to 1, 0, which is negative g, s. Okay, g is positive and s is positive. So negative gs is a vector that points to the left, since the first component is negative, and up, since the second component is positive. So it actually points something like that, as opposed to, you know, to the left and down, or to the right and down, or to the right and up. It points something like that. I don't know, like, maybe it's more shallow or more steep. I haven't chosen units for y, so I don't know. But it's something like that. That's enough to know that I have spiraling in like that, right? There's no way I can have this velocity vector and spiral in going clockwise. Okay, so let me go ahead and draw my beautiful picture. Looks like this. And that's at least qualitatively correct. It's spinning in the right direction, and it's having the right long-term behavior. So let's think about the situation where you eat a cookie or something and follow along the trajectory here. So let's pretend you're in this situation where R and S are large compared to the difference between D and G. So you could say this is a situation where the dynamics are dominated by the insulin-glucose interaction, as opposed to being dominated by the background decay of things. So let's say you start out happy and in equilibrium, right? So that's 0, 0. And if you don't do anything and you just let the system play out from there, then you'll stay there forever. That's why we call it an equilibrium. So 0, 0 doesn't mean, remember, that does not mean you have 0 glucose and 0 insulin in your blood. That means you have the equilibrium levels. And then positive of either means excess, and the negative of either means you have a deficiency. Okay, then let's say you eat a cookie. Okay, the differential equation does not model you eating the cookie, right? Eating the cookie is a separate thing, and then it's going to create some new initial conditions. So you eat a cookie, suddenly, let's say after you finish eating the cookie, you jump and you're here. So you now have excess glucose. So what happens now? Let's zoom in a little bit. So this green point is where you, right after you ate the cookie. Let me zoom out so you can see X and Y there. And then what happens is you go up this way, right? So what's happening is Y is increasing, so you're going up, right? You're going up, insulin levels are increasing. But you're also going to the left. Glucose is decreasing for two reasons. Due to its natural background decay towards equilibrium. You know, your body has other ways of flushing out glucose other than using it due to what insulin is saying it should. Yeah, you get what I mean. So there's two things causing the glucose to decrease: the background decay of you just flushing it out without the help of insulin, and then there's what insulin is doing. So that's why you're going to the left also. So you go up and to the left. Okay, and you keep generating more and more insulin, so you continue to go up as long as you have excess glucose. So as long as you're to the right of the vertical axis, you continue your journey upward. Until, here's an interesting point. Now your glucose levels have gone back down to the equilibrium, the desired level, kind of. I keep saying equilibrium, but I don't mean equilibrium for this system. So when I say your glucose levels are at equilibrium, I mean they're at what would be equilibrium if there weren't insulin doing anything. So your glucose levels here are at equilibrium, ignoring what insulin is doing. But now your insulin levels are kind of high, right? You have excess insulin. So the insulin is still there, and it's continuing to make your body take the glucose out of your blood. So you continue losing glucose. Now you're going to become deficient. Because the insulin does not disappear immediately, right? It takes time. So the insulin signal is still there, and now you're becoming deficient in glucose. You're going to the negative X side of things. But the insulin levels do decay. And they decay faster and faster the more deficient you are in glucose. Until you reach here. This is pretty interesting. So here, your insulin levels have finally gone back down to equilibrium. But now you're deficient in glucose. So your insulin levels really need to decrease below what would be equilibrium for insulin so that you can start generating glucose. I don't know if you actually would be generating glucose. To be honest, I don't know enough about human bodies to know if they can even do that. But maybe it just represents flushing out glucose more slowly or something like that. So your blood glucose levels increase until you reach this other interesting point where finally your glucose is back at equilibrium. But by now your insulin levels have decreased below what they should be, and so that allows your glucose to continue to increase. It overshoots the mark. So each time you're overshooting the target because you have these delayed signals. So you overshoot the mark, and then you're back to the post-cookie situation, but hopefully with less extreme of a starting point. And the cycle continues, and then you're back to the post-cookie situation, but with less extreme of a starting point. And in the long term, you go down to equilibrium. So it's pretty interesting. If you were to plot with respect to time, like what people call time series plots, if you were to plot just glucose levels, excess glucose levels or excess insulin levels against time, then you would see kind of oscillation, right? So these are these kinds of plots. Stuff like that. I guess let's say your initial condition is here, then your glucose levels are starting out positive. So cookie, you start out like this with your insulin levels. I guess we're starting insulin from zero, from equilibrium level here. So maybe something like that with this decaying envelope. Okay, so you get these kinds of oscillations when either R or S are big compared to this other thing. What about when R and S are small compared to this? Or let's say when D and G are very different. This is like the difference between this is like a measure of the distance between D and G, kind of. So if D and G are very far apart, if the decay rates, the background decay rates of X and Y are very different, then I think this is kind of saying like, oh, your body's background ability to send glucose or insulin to equilibrium that isn't due to the interaction between the two is dominating the situation, as opposed to these dominating the situation. So to draw a qualitatively correct picture of a stable node, we really need to know where the eigendirections are, right? We need to know about the eigenvectors. Okay, so we totally could compute the eigenvectors. We just have a bunch of variables, G, R, S, and D in there, but that doesn't prevent us from computing. We could tell Mathematica to do it, but we get giant ugly things that we now have to think about. Actually, to be honest, when I ran this command, I didn't know exactly what to expect, but now that I look at this, it's not as giant and ugly as I thought it would be. And we might actually be able to do something with this. So let me see if I can come up with something to do by hand here. Okay, so I was able to do something with it. So we could totally get these by hand, but I just I used eigensystem to cheat a little bit and get the eigenvalues, these two, and eigenvectors, and I've written them more nicely so I can think about them a little bit. Here are the eigenvalues. You can see this thing under the square root that we had looked at before, and here I'm thinking about the stable node, this case where I have this inequality. This guarantees that what's under the square root is positive. So these are positive numbers, and then I got these eigenvectors, and these also under the square root are positive. So everything here is real. And the eigenvalues are negative. They're negative numbers, as was supposed to happen, as was expected when we observed that the trace was negative. The trace of the matrix was negative. So no surprise there. But one bit of information that might be useful to note is that lambda 1 is more negative. So the difference is the sign here. Lambda 1 is something negative, but more negative, since I'm increasing the magnitude of what's in the parentheses rather than decreasing it here. So I could just write, lambda 1 less than lambda 2, but I find that confusing to think about since they're negative. So lambda 1 is the one with higher magnitude. It's more negative than lambda 2. Okay, and then v1 is the eigenvector that goes with lambda 1. And I just want to draw something that roughly points in the correct direction. So how about I just point out whether each component is positive or negative. So the second component here is definitely positive. 2s is positive. All the parameters, d, g, r, s, are positive. And then what about here? Is this number positive or negative? So I'm taking d minus g, and then I'm subtracting this thing. If you think about it, this thing is less than Okay, hang on. So this thing is in magnitude, in absolute value, it's less than d minus g. But d minus g itself could be positive or negative. So it looks like we could get two qualitatively different pictures depending on whether d is bigger than g or d is less than g. So how about I pick one of those and just draw that one for the sake of doing less work. So let me just pick one. For picture, let's assume, I don't know, how about randomly, let's say your body tends to flush out insulin more quickly than it flushes out excess insulin, more quickly than it flushes out excess glucose. So d is bigger than g, let's assume. Then this is negative, and I'm subtracting something from it, so this is negative. Okay, so this is just kind of a crude notation to point out which direction to draw my vectors in. And then here, 2s is positive, and then this is negative, and I'm adding something to it, so it could be negative or positive depending on, I could end up with something negative or positive depending on how much I add to it. But what I'm adding to it is smaller in magnitude, I think, than it, so it remains negative. Okay, so now if I want to draw these vectors in the right places, like, okay, now I'm wondering, is it like v1 is like this and v2 is like that, or vice versa? Or, sorry, no, negative first component, so they point to the left and up. So is it like this, v1, v2, or is it like this, v1, v2? I don't know. I guess I can see that they have the same second component, so that's handy. So the vectors I'm thinking about go up by the same amount, and the question is just how far to the left do they go? So this number is negative. I would say this number is less negative. So it's more like this, where v1 has a more negative x component, first component, and then v2 has a less negative, so it points less to the left. Whew, okay, that's very confusing. It's very likely I made a mistake. There are many places where I can just flip things around. But let's just draw them in. So here's the line for v1, here's the line for v2. So v1 is like pointing along here, and v2 is pointing along here. And then let me label them by the eigenvalues that go with them. So this one goes with lambda 1, and this one goes with lambda 2. All right, now I care about getting them in the right order because I know that lambda 1 is more negative than lambda 2. So remember what solutions look like? They look like some combination, like C1 e to the lambda 1 v1 plus C2 e to the lambda 2, oh sorry, t, that's where the time dependence is, t v2, kind of like that. If lambda 1 and lambda 2 are both negative, so both of these are decaying, so all solutions go towards 0, including, by the way, the eigensolutions, the ones along these straight lines. But one of these terms decays faster than the other, right? Which one decays faster? The one with the more negative decay rate. So this decays faster. So that means that in the long run, as t goes towards positive infinity, you expect solution trajectories to be parallel to v2. In the long run, this term becomes negligible much more quickly than this one. And this will dominate the direction in which solutions are traveling. So as t goes towards infinity, as you look towards the future, trajectories both go towards the origin, and they tend to be in the direction of v2. So they tend to be parallel to this line rather than the other line. So they come into the origin sort of parallel to this line, like this. And if you look towards the past, flipping around all the reasoning and dealing with all the minus signs, as you send t towards negative infinity, this term will actually dominate and trajectories will be parallel to v1. So trajectories come in sort of tangent to this one, like towards the future, and then in the past they're parallel to this one, so like that. So I guess something like this. And then let me put one in each region. So here, and then towards the past it was more parallel to lambda 1, something like that. Like that, and in the past it was more parallel to, sorry, v1, not lambda 1, v1. And like that. So you can, if you want, you can play out the same story where, you eat your cookie, then you start here, and then you tend to do something like that. And it's similar to this story over here, right? It's just that you can only overshoot up to once, instead of here where you overshoot, overcorrect, 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 and then you just repeatedly overcorrect, but by less and less each time. Here you can overcorrect, but basically just once, and then you decay towards the right place. And this is what's happening when your natural decay rates are high enough, or not high enough, different enough, I guess, or maybe better to say your sensitivity is low enough. Yeah, I don't know. There's not one simple way to put things, I guess. This is pretty complicated. Okay, and I definitely think, this was for d greater than g. The g greater than d picture would be different. I guess if g is greater than d, if you flush out glucose more efficiently than you flush out excess insulin, then what would have been different? I guess these would have been positive. These vectors would have pointed to the other side. You would have had like these rather than the ones we had here. Okay, I hope this was fun. I certainly enjoyed it. I didn't think we could analyze this situation